All right, hello everyone. I hope that you're doing well. So we'll be getting into the introduction to physical science. The reference will be Physical Science by Bill Tillery, 10th edition. I did get an email stating that it won't be printing any new textbooks for that edition. However, you can go up or down in addition to the ninth or the 11th. The chapters should be similar, so the material will be the same. As you can see, they're still used copies. You can rent, um, but this is what I'll be referencing. All right, so let me go back. All right, so again, these slides are summarizing what is in the chapters. However, it's not a substitution for, reading the actual book. You're going to get the most knowledge from those readings of the chapters. All right, so introduction to physical science first. Well, what is physical science? It's just a search for order in our physical surroundings. So you can count that as our environment here on Earth. You can count that as substances and objects out in space. All right, so the concepts covered in physical science are several different subject areas. So, like the first 7 chapters are physics, the next couple of chapters are chemistry, after that is astronomy, and then earth science. So, we'll be talking about a lot of different subject areas within one semester. All right. All right, so the first topic is the SI unit system. SI stands for the International System of Units. This is what the rest of the world uses for their fundamental properties. Um, However, here in America, we have slightly different measurements that we use. However, in the scientific community, we do use these SI fundamental unit properties. So make sure that you kind of familiarize yourself with these because we will be going over them over and over. You will see these throughout the semester. So just go ahead and practice that repetition of learning uh, to make this stick into your mind. All right, so length, which is just the measurement between 2 points. For the SI unit, measurement of length or distance is going to be in meters. And then the SI unit abbreviation for meters is lowercase m. Mass is denoted by the symbol lowercase m. So try not to get, it's a lot of these letters that will be used and reused. So make sure you know the difference between a property symbol and the SI unit abbreviation symbol. All right. So the SI unit abbreviation symbol is just a shorthand version of the measurement. And the property is kind of like a shorthand version of that fundamental property. Okay. So symbol for mass is lowercase m, measurement is in kilograms. The SI unit abbreviation for kilograms is lowercase kg. Time is lowercase t, measured in seconds. So that would be the abbreviation lowercase s. And then temperature, represented by capital T, is in Kelvin. And the SI unit abbreviation for Kelvin is capital K. Now, as you can see, these measurements are not things that we are familiar with here in America. So for distance, we usually use miles. Here, sometimes we confuse mass with weight, so we would use pounds. Temperature is usually, temperature is actually usually in Celsius or Fahrenheit, and then time is in minutes or hours or something like that. So please keep these in mind. For physics, we are using the fundamental properties unless otherwise noted in your homework, test, or quiz. All right, so familiarize yourself with these base units. The rest of the properties that we come across throughout the semester will build upon the fundamentals. Okay, so it's going to be hard to go further without really getting an understanding of this right here. All right, so the scientific method, you will need to know this. It will appear on your homework, tests, quizzes, even the final exam. So if you go ahead and learn this now, it'll come easy to you when it really, really counts. All right, so the first step in the scientific method is to make observations. So this is that just you observing the environment, seeing a problem that you're trying to solve. So you define the problem. And second, you're going to gather data about that problem. You need to make sure, and we do this during a literature review, make sure that the problem hasn't already been solved, because you don't want to do something that has already been done. Okay, that is a waste of time. So you want to do something new. Okay. Next, you want to make a hypothesis, which is just an educated guess on what you think may occur during your experiment. Then you will test your hypothesis by performing the experiment. All right. And once you perform your experiment, your results will give you either one or two things. Either your experiment agrees with your hypothesis, and in that case, you would retest to make sure that it's not a fluke. If it does not agree with your hypothesis, however, you will have to figure out what went wrong, or you will have to revise your educated guess. Okay. So if your experiment does match your hypothesis, you have to perform that experiment more than once, so multiple times, in order to draw proper conclusions from those results. And if each and every test passes, you would be able to establish a law or theory. Now, if it doesn't pass those test results, you pretty much have to revise your hypothesis or figure out where you went wrong. Okay. All right. Next, we will talk about density. All right, so density is a ratio of the mass to the volume of an object or substance. Okay. So the equation for density is mass divided by the volume. So the lowercase property symbol for mass is lowercase m, and then volume is capital V. So let me go to the whiteboard so we can kind of draw out what the symbol for density is. Okay, we'll be actually coming back to volume. So let me leave that there. And let me get to a new whiteboard. Let's do the color in black. All right. So density. And please excuse my chicken scratch. It is an adjustment to write with the tablet and the pen. Density. Make sure I'm doing this as best as possible. All right, so the Greek symbol for density is the Greek letter rho. Looks like a P, but it's not a P. Sometimes if you want to just do capital D, I'll know what you're talking about, because you're referring to density. Most of the fundamental properties use the first symbol, usually, for that fundamental property. All right, so again, density, which is denoted by the Greek letter rho, again, looks like a P, not a P, is mass divided by the volume. All right, so sometimes you'll see the density equation written as lowercase m over capital V. All right, and your mass is usually in kilograms. That's the SI unit for mass. And then your volume is usually in meters cubed. That is the SI unit for volume. And that's where this last whiteboard comes in, where I break down volume, which is length times width times height. All right. And the SI unit for length is meters, width is meters, and height is meters. So meters times meters times meters is going to be meters to the third power. So M, you're assuming that the exponent here is 1. So M to the first power. And then you just kind of add those up, 1, 2, 3, and that's how you get meters cubed here. All right, so here I was just going to show where you have like a standard square right here. You have your length and you have your width. And to turn a 2D area into a 3D area, you would just add your third dimension to make your area turn into volume. So right now I'm just turning a regular 2-dimensional square into a cube here. So this is just for your visual reference for volume. Okay, so let me go back to the slides. So again, the SI unit here, and let me put that in a different color. So the SI unit is going to be kilograms over meters cubed for density. And what you'll learn here in the physics section of this book is that when you answer these equations, make sure that you are putting your SI units, or you will be missing out on valuable points. Those points add up over time. All right, so again, density, the ratio of mass to volume of a substance. All right, so here I got a couple of examples. The density of water, nearly 1,000 kilograms over meters cubed. Density of ice is slightly lower at 917 kilograms over meters cubed. Density of air is 1.225 kilograms over meters cubed. And the density of cooking oil ranges. So this depends on what type of oil it is, whether it's vegetable oil, coconut oil, olive oil. All of those have slightly varying densities, and it ranges from 870 to 920 kilograms over meters cubed. So the main point about density is to remember that the substance with less density will always float on top of the substance or object with higher density. All right, so higher density sinks, less density floats. So if you've ever mixed oil and water before, as you can see here, water is more dense, so it would sink. Oil is less dense, so it would float. Anytime you see the kids in the kiddie pool and they have like the flotation devices that are filled with air, because air is less dense, it will always float on top of the water. So this reduces the probability of drowning. Anytime you have ever had a glass of ice water, you will notice that the ice will always float on top of the water because the ice is less dense than the water. So more dense sinks, less dense floats. All right, that will be a question in the future. All right, so that was chapter 1. Chapter 2 is on motion. And motion is just the movement of whatever object or substance that you are observing in nature or your surroundings. All right, so events such as moving clouds, rain falling or snow falling, a river of water, or a body of water that's moving. All right, those are types of motions. All right, so motion involves a change in position over the passage of time. Okay, so again, change in position. We usually describe these two combinations of position and time with the properties of length, which the SI units for length is in meters, and then time, which is the SI unit will be in seconds. All right, so The three properties of motion that we'll be discussing is speed, velocity, and acceleration. So speed and velocity, these two words can be, or they are interchangeably used. However, they mean slightly different things. All right, so your speed is your distance over time, or your velocity is your distance over time, or the change in distance over the change in time. All right, so the units for speed and velocity here, the SI units would be meters over seconds, but in several different countries, you'll see kilometers over hours or miles per hour, which is what we use here in the US. All right. All right, so the difference between speed and velocity. Speed is a scalar quantity and velocity is a vector quantity. So a scalar quantity is just a numerical value. Velocity, which is a vector quantity, this has a numerical value as well as a direction. Okay, so let's say I'm on the highway and I'm traveling at 50 miles per hour. That would be my scalar quantity or speed. But if I tell you I am on Interstate 40 traveling in the eastward direction, and I'm going at speed of 50 miles per hour or meters per second, I'm giving you not only my scalar quantity, but I'm also giving you the direction. All right, so the interstate direction gives you the direction, and then the speed is your scalar quantity. So speed, just the numerical value of how fast you're going, and then velocity is how fast and in what direction. All right, acceleration and free fall. All right, so the change of velocity over time. This is what we call acceleration. All right, and then free fall, this is your downward motion of objects towards the Earth's surface. We also call free fall gravity, and gravity is a form of acceleration in the downward direction towards the Earth's surface at 9.8 meters per second squared. So let me go to the whiteboard. Let's clear some things off and start from scratch. We have a clear. All right. And let me go to black color. Okay. All right, so we have learned about velocity. Don't sign in, leave me alone. All right, velocity, and now I changed my color. All right, let's go back. Velocity. All right, the symbol for velocity, lowercase v. Volume would be uppercase V. All right, and your velocity is the distance traveled divided by time traveled. Technically, this would be your speed, distance over time. So your velocity would be your change in your distance over the change in time. All right, so since this is not a calculus-based course, we won't be going too in-depth on this. Just know that your final distance minus your initial distance is divided by your final time minus your initial time. That's what this represents. So let me not confuse anyone. All right. So again, speed and velocity. are interchangeably used. Speed is your scalar quantity, which is the numerical value. And then your velocity is your vector quantity, And please ignore my chicken scratch. It is hard to kind of write on imaginary lines here. Let's see. Vector quantity, and this is your numerical value and your direction. So it not only represents how fast, but also what direction is the movement of that object or substance. And then speed is just how fast. Okay, so let's go back to the slides. Okay. All right, so acceleration, let's get to the whiteboard and do free fall and acceleration. So let me erase this. All right, and I don't want orange. Okay, acceleration, leave me alone. And free fall, also known as gravity. Okay, so your acceleration is denoted by the letter A, and it is your change in the velocity over the change in time. So again, I'm not going to go into the calculus of this because this is algebra based, so I don't want to confuse you with those delta symbols. So it'll be your velocity over time, and free fall, which is your gravity. Gravity is denoted by lowercase g, and it's equal to 9.8 meters per second squared. All right, so let's discuss SI units. So we know that distance is in meters, and we know that time is in seconds. So the SI unit for velocity, SI unit for velocity is going to be meters over seconds. So if we go back to acceleration, we see that velocity, let's change the color. Our SI unit here, I can go down here, SI unit for velocity is going to be, for acceleration is going to be our velocity, which is meters over seconds, divided by time, which is in seconds. All right. So meters over seconds is going to be equal to meters over seconds squared. This is the SI unit for acceleration. It is also the SI unit for gravity, because gravity is a form of acceleration in the downward direction towards the Earth's surface. All right, so gravity is downward acceleration. All right. Okay. So the difference between velocity and acceleration is that acceleration is velocity over time. So you're trying to see how much you are speeding up slowing down, or staying at a constant rate of change. All right, let's go back to the slides. All right, so next we're going to talk about forces. A force is just simply a push or pull on an object. All right, and the net force is the sum of all the forces acting on that object. And there's different types of forces. You have 4 fundamental forces. Since this is a introductory level, we won't go into a lot of detail right now about this, but you will see this a little bit later in the physics chapters. So you have gravitational forces, electromagnetic, and strong and weak nuclear forces. So again, we'll go into a bit more detail later. But let's head to the whiteboard and let's clear this off. Instead of doing that, I wish they had, oh, there it is. Make sure you want to erase the entire board, erase all. It did not erase all. So I could just keep scrolling down. I don't have to delete anything. It's my first time using this one. All right, so on to force, which is simply a push or pull on an object. The symbol for force is capital F, and force is equal to mass times acceleration. So the mass of the object times the change in velocity over time, which is what acceleration is. So the symbol for mass, lowercase m, symbol for acceleration, A, and then our SI unit for force would be kilograms times meters per second squared. All right, kilograms times meters per second squared. All right, so your mass is in kilograms, your acceleration is in meters per second squared. This is also known as a Newton. This is named after Sir Isaac Newton, who is known as the father of physics. All right, so the shorthand property for Newton is capital N. And again, force is simply a push or pull on an object. All right, so back to the slides. All right, moving on to the difference between mass and weight. All right, weight is the downward force that results from the Earth's gravity acting on the mass of an object. So your mass is going to be, your weight is going to be your mass times the effect of gravity. All right, this is similar to force, and I will show that right quick. All right, let's scroll down. All right, so weight is going to be mass times gravity. All right, so weight is equal to m times g. All right, so if we go back to our SI units, the SI unit for mass is kilograms, and the SI unit for gravity, which is a form of acceleration, here we see that both of those SI units are the same for both acceleration and free fall gravity, meters per second squared. Meters per second squared. Also known as a Newton, which is what we just discussed in force. So if we scroll back up, didn't mean to do that. We scroll back How do I scroll back up? That's not working. Okay. Oh, there we go. All right. So weight is a form of force in the downward direction towards the Earth's surface, which is why they are similar and have the same SI units. All right, so let's go back to the slides. All right, so most of the time here in America, we measure weight in pounds. All right, but the SI unit for weight is actually in newtons. Okay, so again, gravity, lowercase g, is 9.8 meters per second squared. And let me this bigger. So the property of mass is sometimes confused with weight, but they do mean separate things. All right, so mass is an object. This is a measure, the mass of an object is the measurement of inertia of that object. And inertia is the tendency of an object to remain in unchanging motion, whether it's at rest or moving, in the absence of an unbalanced force. All right. Next, we're moving on to Newton's 3 laws of motion. The first law is that every object, whether in motion or at rest, remains in that state unless it's acted on by an outside force. Unbalanced force here just means outside external force. The second law is pretty much this equation you see here, which we just discussed. Force is equal to mass times acceleration. Number 3, for every action, there is an equal and opposite reaction. That is the third law. All right. Next is momentum. Momentum, the symbol for momentum is lowercase p. I know this is going to be confusing, but we've pretty much already used lowercase m for mass. So I guess that's why it's lowercase p. Well, I can't really explain it because I would have used like a capital M or something like that. But momentum is denoted by lowercase p, and it's defined as the product between mass, the product of mass of an object times the velocity in which it's moving. So momentum is mass times velocity, or P is equal to mv. And the SI unit is mass, which is in kilograms, times velocity, which is meters per second. So the law of conservation of momentum it states that the total momentum of a group of interacting objects remains the same in the absence of external forces. So if you've ever seen a basketball game where, especially pre-COVID, where the player would rush down the court to try to hurry up and get to the goal post to make the shot, sometimes their momentum is so high that they can't slow down after they make the shot. It kind of ended up in the audience, running into, people on the front lines of the audience. All right, that's an example of momentum. So it's the mass of an object times the velocity, or how fast it's moving. Okay, and then last but not least, circular motion forces, which I usually try to save this for the more advanced physics courses, so I won't make you memorize these here in the introductory level. But just for your information, centripetal force, this is the force that pulls an object out of its straight line path and into a circular path. The centrifugal force is the outward force of circular motion. And then the universal law of gravitation states that every object in the universe is attracted to every other object with a force. And that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So that is a whole equation that we will not go too deeply in the introductory level course. All right, so just for your information, but won't be on your test. All right, so I'll start right there as far as the lecture goes.